Most students can plug numbers into formulas, solve exercises, and pass tests about functions, yet many confess they've never truly grasped what a function is. That may feel surprising, even paradoxical. Today, we change that. By the end of this lesson, the idea of a function will be simple, useful, and dependable. We'll proceed carefully, every symbol, every comma, every reason explained. Picture a compact machine. Feed it an input. The machine follows its internal instructions, then ejects an output. That image captures the essence of a function, a mapping that takes something in and produces precisely one thing out. For example, consider a machine that multiplies any number by 3. Put in 2, out comes 6. Put in 5, out comes 15. Identical rule, consistent results. Simple, elegant, reliable. In mathematics, we like tidy notation. You'll often see a function written as f of x equals 3x. Read it carefully. F is the name of the machine, merely a convenient label. The name can be anything. You'll see g, h, t, or named functions like temperature. And f is convenient because it is the first letter in the word function. X names the input variable. X is a placeholder, not a special number. We might just as well write g of t or temp of c. The symbol inside the parentheses indicates where the input is placed. It's customary because of history and habit, but any symbol works. Use T for time, C for Celsius, N for a counting number. The important point is that the symbol marks where the input appears in the rule. On the right-hand side, 3x describes the rule the machine applies to that input. So f of x equals 3x. It is read as, apply f to the input x and return 3 times x. If the input is 4, we write f of 4, and evaluate f of 4 equals 3 times 4. Substitution is the single, straightforward operation you'll use every time. Replace the placeholder with the given input, then compute. And this is the result for the function called f, if we have 4 as input. Some functions consist of a single tidy instruction. Others are assembled from a set of rules that each apply in particular circumstances. For instance, this is one function with 2 rule blocks, a square for non-positive inputs and a linear rule for positives inputs. What matters is consistency. For every allowed input, the definition prescribes exactly one output, even if the prescription changes depending on the input's category. The defining feature of a function is this. Each declared input yields exactly one output. If a rule may produce different outputs for the same input, it is not a function. However, it is entirely acceptable for 2 different inputs to yield one and the same output. Mousie thinks it's best to try the function for yourself early on. It helps the ideas settle, so that's what we'll do. Here's the function we used earlier. I'll give a few inputs. You'll calculate the output for each. To keep things tidy, we'll write inputs in one column and outputs in another column. Pause the video and try to solve them. Ready? Let's take a quick look. For negative numbers or equal to 0, we used the first calculation formula. And for numbers greater than 0, we used the second calculation formula. And so we obtained a series of results. Now that we have listed inputs in one column and outputs in the other, let us put those columns into mathematical language. We begin with the set of inputs. From now on, we will call that set the domain. In plain terms, the domain is the set of values you are allowed to feed into the machine. If a candidate input would force a mathematical paradox like dividing by 0, it must be excluded from the domain. Hence, domain is not a vague idea. It is a precise list of permitted inputs. All right, let's carefully read what we have here to make sure everything is fully understood. We are looking at this function. Let's break it down piece by piece. First, the name of the function is f. The letter x inside the round brackets is simply a placeholder for the input. After the equals sign, we see the rule that defines the function. Take one and divide it by the input. Now, the abbreviation DOM stands for domain. As we mentioned earlier, the domain of a function is the set of all inputs for which the function makes sense. So here we read, the domain of f is the set of all real numbers x, such that x is not equal to 0. Let's pause and unpack every symbol. The curly brackets mean we are describing a set. The expression x belongs to the set of real numbers. The vertical bar, sometimes written as a colon, is read as such that. It tells us that there is a condition. The condition is x is not equal to 0. A shorter way to write the same thing is dom f equals r\0. 0 between the brackets means the set that contains only the number 0. The curly brackets are used to describe sets explicitly by listing their elements inside. For example, 1, 2, 3 is the set containing exactly those 3 numbers. In our case, 0 is a set with just one element, 0. The symbol backslash is called the set difference. It's read as minus in the sense of sets, or more formally, a set without the elements of another set. So if we write A\B, it means all the elements of A, except for those that also belong to B. Here, we have R\0. That reads, take all real numbers, but remove the element 0. Next, we name the world where outputs live. When we define a function, we usually declare a target set for its outputs. That declared set is the codomain. Think of the prefix co as signaling partnership. Codomain is the domain's companion. Declaring a codomain is part of the function's definition. You are stating in advance the universe in which you expect outputs to appear. Mathematics compresses these two choices into compact notation, writing f(a) to b. Means f is a function with domain A and codomain B. Read symbol by symbol, f names the rule. The left hand A is the domain, allowed inputs. The arrow reads maps to or produces outputs in, and the right hand B is the codomain, declared target set. Apply this to our running example. We defined a natural declaration is fr to r. From what we understand, that f is a function from the real numbers to the real numbers. That tells the listener two things at once. Any real number is an allowed input, and we regard outputs as real numbers. In our case, any real number from -infinity to +infinity is accepted as a domain and also as a codomain. So far, we've talked about the domain, the set of all possible inputs, and the codomain, which we can think of as the target space of outputs. But here's the thing. The codomain can often feel too large and too vague. For example, in this case, we said the codomain is all real numbers, stretching from -infinity to +infinity. That's a huge set. The question is, do we really need all of it? Not quite. What we usually care about is not every number that could exist in the codomain, but the numbers that actually do come out of the function when we apply the rule. That specific set of real outputs is called the range of the function. Think of it this way. The domain is what goes in. The codomain is where the outputs are allowed to land. The range is where the outputs actually land. And being precise about the range gives us much more information. Let's apply this to our function. For inputs less than or equal to 0, the rule is x squared. Squaring any non-positive number gives us a non-negative result. In fact, the smallest value here is 0, which happens exactly at x equals 0. So this part of the function produces outputs in the interval 0 and +infinity. The square bracket on the left means the endpoint is included, so here 0 belongs to the set. In other words, the range actually contains the value 0. The number 0 is the starting point of the interval. That tells us the smallest possible output of the function is 0. The comma separates the two ends of the interval, the starting point on the left and the direction we are going on the right. The symbol infinity does not represent a number you can reach. It's more like a direction that goes on forever. So here, it means continuing upwards, without bound. The round parenthesis on the right means the endpoint is not included. And that makes sense. We can get values as large as we want, but we never arrive at infinity. It's not an actual number, just a concept. So when we put it all together, 0, infinity means all real numbers greater than or equal to 0, extending without limit towards positive infinity. For inputs greater than 0, the rule is 2x plus 1. When x is just barely above 0, say 0.0001, the output is just above 1. As x increases, 2x plus 1 grows without bound, so this part of the function covers outputs in 1 to infinity. But be careful with the round parentheses. As I said earlier with the parentheses at infinity, here it's the same situation but also with 1, because in our case, any number greater than 0, even the smallest one we can think of as an input, will result in an output greater than 1, because we have that condition to add 1. So for this set of rules, the range will be between 1 and infinity, but the round parentheses means the endpoint is not included, so 1 is excluded. Now that we have defined the possible output for both rules in the function, we can combine them and find the actual range of the function. Notice how the second piece, 1 to infinity, is already contained within 0 to infinity. Thus, the entire range of the function f is from 0 to infinity, including 0. So even though the codomain was all real numbers, the range is much smaller and far more precise. Let us create a hypothetical situation where we need to use a function. Suppose that somewhere in a laboratory, a thermometer measures temperature in degrees Celsius. The thermometer can measure values in the interval from -40 up to 100 degrees Celsius. However, the laboratory technician needs the temperature in degrees Fahrenheit. For this, he uses a computer program that automatically converts Celsius into Fahrenheit. The conversion follows this rule. That is, we multiply the Celsius temperature by 9/5 and then add 32. The result will be the temperature in Fahrenheit. We want to describe this situation using a function. We will call the function f with a capital letter because it outputs Fahrenheit values. Let's see together what the function that converts degrees Celsius to degrees Fahrenheit looks like. The input is C, the temperature in Celsius. The output is f of C, the result of the function f, which takes C as its input and gives the corresponding temperature in Fahrenheit. And we have the rule, 9/5, C plus 32. Let's test the function with an example. Suppose the thermometer shows 20 degrees Celsius, then f of 20 equals 9/5 times 20 plus 32. We do the math and get f of 20 equals 68. So 20 degrees Celsius corresponds to 68 degrees Fahrenheit, which is correct. So our function works. Now let's define the domain. The thermometer can only measure from -40 degrees Celsius to 100 degrees Celsius. Therefore, the domain of the function is dom(f) equals -40 and 100. We use right brackets. This means the input values are all real numbers from -40 up to 100, including both endpoints. With all this information, let's find the range of f. We look at the smallest and largest input values, in this case, -40 and 100, because the thermometer cannot measure other values outside this range. So I'll let you calculate the function given these two values as input. When you're done, we can continue. So the minimum value is -40 degrees Fahrenheit, and the maximum value is 212 degrees Fahrenheit. Thus, the range of f is between -40 and 212, including both endpoints. That brings us to the end of Part 1, Function, Domain, Codomain, and Range. See you in Part 2.